Let's take a look at another example for Module 12 for ME12 Dynamics course. So in this problem here, we can see we have a spool. You can see the outer rim here is at a radius of 0.5 meters. The inner hub here is at 0.2 meters. There's our center of mass at G right there. You can see we have an external load over here of 100 newtons. Now, in our problem statement, it tells us that the spool has a mass of 8 kilograms and a radius gyration given to us as 0.35. They also tell us that the chords are of negligible mass, so we can ignore the mass of those, and they're wrapped around its inner and outer rim and hub. They also tell us that there is no slipping as one of our assumptions. So what do they want us to solve for? They want us to find the angular acceleration, or our alpha term, of the spool. So our plan of attack for this problem here is we're going to focus on the spool itself and follow our general procedure again that we've seen in our lecture slides here and draw out our free body diagram, equations of motion, and identify our unknowns. So now that we've had the opportunity to read through that problem statement, take a look at our initial given diagram, our next step in the process is to create our setup page. So on our setup page here, what I do is I redraw out my given diagram in a simple 2D version here, so I can look on this head on. I can see, okay, I have my weight here at the center of gravity, which I can calculate from my mass times acceleration due to gravity. I have a tension force over here. I have my external force over here. I have my center hub here, and I have my radius of the center hub and the outer rim, respectively there. Given, have my k sub g, my radius of gyration is 0.35 m. My mass of the spool is equal to 8 kilograms. My weight is equal to mass times acceleration due to gravity, or the 8 kilograms times my 9.81 meters per second squared. So therefore, my weight, when I do that calculation out here, I'm going to do that right on my setup page so I have it readily available to reference back to, is 78.48 newtons. Now, what are they asking me to look for? I write down here, they want me to find my angular acceleration, or my alpha, of the spool. And I'm going to focus here as I begin my solution on the spool, go through my whole procedure with the free body diagram, equations of motion, and figure out what my unknowns are. So my procedure for analysis, I'm going to go through this again. It's in our lecture notes, but I want to go over it one more time as we're going through the solution of this problems. So any problems involving kinetics of a rigid body undergoing general planar motion can be solved using the following steps. So step one, what we want to do before we even start this problem here is establish an initial XY coordinate system here. So what do we want to choose as a positive X? What do we want to choose as a positive Y? We want to draw both the free body diagrams and the kinetic diagrams according to our chosen coordinate system here as well. Next, we want to specify the direction and the sense of the acceleration of the center of mass. So what is our a sub g? And the angular acceleration, our alpha, of the body. If necessary, we want to compute the body's mass moment of inertia, our I sub g. We may need to look this up for what the I sub g formula is from our tables for whatever shape or object we're using. 3, we want to come up with our moment equation now. So summation of moments around some point is equal to whatever equation we're using here. This is just in general terms. Use our kinetic diagram to help us visualize the moments developed by the components, our ma sub gx, ma sub gy, and our I sub g alpha. Fourth, we're going to apply the 3 equations of motion. So as we continue on here, step number 5, we want to identify our unknowns. Do the number of equations match the number of unknowns? If they don't, we need to come up with another equation, another relationship, so that our number of equations match the number of unknowns. Some of these could be our slip-no slip assumption, or our use of the a sub g is equal to alpha r, and equations and relationships like that. We could also use our kinematic equations as necessary to complete the solution. So if we need to solve for velocity, acceleration, position based off of those relationships, we can call back to our kinematic equations for that. 7, if we do a no-slip slip assumption, make sure we double check its validity. So if we assumed no slip and it's really a slip and it doesn't check, make sure we go back and make those changes. So things to consider, make sure you're consistent with all your directions. So the direction of AG must be consistent with your directions of alpha. If you choose a given coordinate system, make sure you stick with that and do the correct sign convention. If you're using frictional force F sub F here, and you have your is equal to mu sum k times your normal force, again, recall that the relationship your F sub F must oppose the direction of motion. So now as we begin our solution here, first thing we want to do is calculate our moment of inertia of the spool. Now we're given our k sub g, our radius of gyration here, in the problem statement. We have a numeric value for that. So we can use this relationship here that our k sub g is equal to the square root of our I sub g divided by m. So we can rearrange now and solve for our I sub g. So we can square both sides of this. We end up with k sub g squared is equal to I sub g over m. Then we can take this m here, multiply it over to this side here. So we get the relationship that I sub g is equal to m times our radius of gyration squared. Plug in our known values. We know our m. We know our k sub g were given to us in our problem statement. So our I sub g is equal to 8 times 0.35 squared, or 0.98 in units of kilograms times meters squared for our I sub g. Now there's a couple different ways that we can solve this problem. In this video solution here, I'm just going to go through method 1, and I'll post method 2 as a PDF and as a hand solution to this as well, so you can compare the two of them. So for method 1, what we're going to do here is we're going to draw out our free body diagram, go through that whole procedure that we just talked about here, establish our coordinate system, draw out our free body diagram, look for our equations of motion from the free body diagram, identify our unknowns. So all those steps that we just went over and are in your lecture slides, we're going to go through here. So first thing we do, we establish our coordinate system here. I'm going to call positive y going up, positive x going to the right. I have my a sub g going up in my positive y direction here. And now I'm going to draw out my free body diagram. So I take my simplified version of the initial given diagram there and add in all my external forces. So I got a tension force over here. I have my external load of 100 newtons there. I have my weight force over here. And I have my associated dimensions here for our inner hub and outer rim. And I have my center of mass right here at G where my weight force is acting. So from this here, I want to do out my summation of motions in order to come out my equations of motions here. So my summation of forces, I want to do my summation of forces to come up with my equations of motion. So my summation of forces, I'm going to say, okay, I look at my free body diagram, and I've only got forces acting in what I'm considering my y direction. I don't have any forces acting in my x direction, so that simplifies it down a little bit. So I can say, okay, left-hand side of Newton's second law, F equals ma, what are the summation of my forces acting in the y direction? Again, recall my y is positive going up. So in the positive y direction, I have my tension force and this external force here of 100 newtons. So I say T plus 100 newtons minus, in my negative y direction, I have my weight force of mass times acceleration due to gravity, which is 78.48. There's my minus sign because I'm acting in my negative y direction, is equal to the second side, right-hand side of Newton's second law is my mass times acceleration. So my a sub g here, so my mass is 8, given to me in my problem statement, times my a sub g is my acceleration in my y direction. So this gives me one equation with two unknowns. I don't know my tension force, and I don't know my a sub g. So my second equation here can come from summation of moments about g. So I go back over here and I take a look and say, okay, what is causing a moment about g? Well, my weight force is not going to be causing a moment about g because that's acting purely at g. So I'm going to have my external load here of 100 newtons and my external load tension force over here times their distances away from my center of mass here, g. So I'm going to have 100 newtons times my 0.2 meters, and I'm going to have my tension force times my 0.5 meters. Now pay attention to my sign convention. They're going to be opposite signs here. So for this one here, I'm going to say that our counterclockwise is going to be negative, clockwise is positive here. So I have 100 times 0.2 as a positive moment, and I have a negative t times 0.5 is my negative moment there, is equal to my right-hand side of the equation, which is my I sub g times my alpha. Well, I've already went through and solved for my I sub g previously, so I can plug that right in there at 0.98. And now I have an alpha term here. So now I have two equations, but three unknowns. My three unknowns are my tension force, my a sub g, and my alpha. So now we can go back to that procedure for analysis we talked about and figure out how to get this third equation. So we need one more equation to solve for these three unknowns. So now what I can do for my third equation here, for my three unknowns, is look here and see that this is a spool that rolls on the coordinate point A right here. And it rolls without slipping, and that's given to us in the problem statement. So we can go back to our procedure here and see that now, because we're making that assumption, which is given to us in the problem, so we don't need to verify it, we have the a sub g is equal to our alpha r. So we can plug that in as our third equation here, plug in our value for r. So a sub g is equal to our r term right here, which is 0.5 times our alpha. So from our three equations here initially, our summation of forces, our summation of moments, and now this third relationship here for rolling without slipping. We now have these three equations and three unknowns. Our three unknowns are our tension force, our A sub G, and our alpha. Three equations, three unknowns. We can solve these guys simultaneously. We could do this by hand. We could plug this into MATLAB. We could even do it in Excel. So if I choose to solve these by hand, I'll go through the procedure for analysis here. So if I want to solve equation 1 for tension, so I take this equation 1 here, I can rearrange it, solve it for tension. When I do that, I can say, okay, I'll move my t over to one side. So t is equal to my 8a sub g minus 100 plus my 78.48. I can combine these two guys together, and I end up with t is equal to 8 times a sub g minus 21.57. So now my equation 1, I'm going to rewrite it here on the top of this slide. Now becomes this over here. T is equal to a sub g time minus 21.52. So I now have that along with my equation 2 and equation 3 here. So my next step here is I'm going to take equation number 3. I'm going to plug this in for my a sub g. So I take this relationship right here. A sub g is equal to 0.5 times the alpha. I can plug in right here for my a sub g into my modified version from equation 1 there. And what I end up with here is t is equal to 8 times, when I plug in for my a sub g, 0.5 alpha minus 21.52, multiply through by my 8. 8 times 0.5 is 4. So t is equal to 4 alpha minus 21.52. So now what I can do with this is I can come back here with this t equation and plug it right into equation 2 for my tension force right there. So I plug in this relationship 4 alpha minus 21.5, plug that right in there for equation 2. So I can see now, okay, my equation 2 now becomes 100 times 0.2 times, and I did it out longhand here from this portion of it right here, 8 times 0.5 alpha, which again reduces down to 4 alpha there, minus my 21.52, minus my 21.52, times my 0.5 is equal to the right-hand side of this equation, 0.98 alpha. So I can do out some math here. 100 times 0.2 reduces down to 20. Now this is times my 4 alpha minus my 21.54, and I plugged in for my tension force there, times my 0.5 is equal to 0.98 alpha. I can distribute this 0.5 through there, and I now have 20 minus 2 alpha minus 10.76 is equal to 9.98 alpha there. Reduce down a little bit further, 30.76 minus my 2 alpha is equal to 0.98 alpha. You can say I have an alpha there and an alpha there. Let's try to get these on the same side. So this becomes 30.76 is equal to 0.98 alpha plus 2 alpha there. Pull out my common term, my common alpha there, so I end up now having 30.76 is equal to alpha times 0.98 plus 2. So 30 plus 30.76 is equal to alpha times, when I add those together, 2.98. Rearrange, solve for alpha. Alpha is equal to 30.76 divided by 2.98. When I do that out, my alpha now has a value of 10.32 in units of radians per second. So what do I do with that there? Well, now I can plug in that I have numeric value for alpha into those equations. So I write out my 3 equations here again. And I realize I have an alpha there and an alpha there that I can plug in this numeric value I've just solved for, my 10.32 radians per second, in for my alpha here with for my tension up there, and in for my alpha here for my a sub g over there. So I plug that in to equation 1 now first, plug in that 10.32. So tension is equal to 4 times 10.32 minus 21.57. So now I can get a numeric value for my tension. Tension is equal to 19.8 newtons. Do my unit analysis, make sure that checks out. Then I can also plug it into equation 3 here. So when I plug into equation 3, I can get a numeric value and solve for my a sub g. So a sub g is equal to 0.5 times that alpha. So I take that alpha of 10.32, plug it in for my alpha value down here in equation 3. What I find here is my a sub g is equal to 5.16 meters per second squared. So that's one possible way of going through a hand solution. There's different ways we could have solved equation 1 and 2 for tension, set them equal to each other. We could have plugged these all into simultaneous equations into MATLAB or Excel, Mathematica, any of those as well. But this was easy enough that I wanted to go through and show you how we could solve this by hand.